Hey everyone, my name is Sophia Pedigo, and today we're going to be looking at um, conducting a von Neumann stability analysis on the equation that we found in our previous videos. So in my last video, we were able to create a plot of the temperature variance for this piece of material that we're working with. But when we started changing the values of R in our collaboratory code, we started getting some really wonky stuff happening with our graph. So this is an attempt to figure out what's going on. I've got a couple of equations here. This one up here is actually one that we derived in my first video, and it just showed that for any value of k, this was a solution for our equation. And this one down here is one that we worked on and actually gives us the temperature profile. That's what I'm looking for, a temperature profile for each value that we're looking at. So what we're going to do is we're going to make a substitution in for x and t up here, because x and t aren't actually like the total temperature or total distance for the material that we're working with and the time frame. So if you remember, we're working with a bar that looks something like this. It's split up into a bunch of little increments. And if we were just to write x, that wouldn't really be the total length of the bar. So we have to write j, which is like the increment that we're using, and then multiply that by delta x. And very similarly, what we're going to do for time is we're going to multiply it by like the length of the increments by delta t. And that gives us the total time here. So I'm going to substitute those up here into this equation, and we're going to go from there. So we end up with t to the j n plus 1. So just for some temperature at some position j at some time n plus 1, that is equal to e where k is just some integer. Now that we have that, I'm going to, let me erase this part so it's a little less confusing because there's kind of a lot going on. Now that I've got that, though, what I'm going to do is I'm going to substitute this one into this one now. So let's go ahead and do that. Let me erase this. And when we do that, we end up getting t to the j n plus 1 Oh, you know what? I forgot to take out this and put that out front there. Here we go. Okay, so now that we've got that equation, what we're going to do, and I'm going to write this kind of down here at the bottom. If you remember looking at Euler's formula in a couple of videos ago, I think it was in my first one, Euler's formula, I think I'm doing this from memory, so this might be off. E to the I x would be equal to cosine x plus I sine x. We're going to apply that same principle up here to this one, except instead of using I to the x, we would be substituting in for e to the ik delta t, or e to the ik delta x. So we're going to do that now. I just wanted to show you where I'm getting this from when I do it, so it's not like I just randomly started changing things. It's based off of Euler's formula. So I'm also going to take out this t j to the n, just so we kind of clean stuff up a little bit. So when we do that, we have the temperature at some position j at some time n plus 1 is equal to, Okay. And that is just what you get when you, again, substitute using Euler's formula. That's what you're going to get. And now we've kind of come to the end of this part of like rearranging. But what we really want to do is look at this little guy right here. And we're gonna do like an inequality basically and solve and see what happens. And that's gonna be able to tell us something about R. So let's get into that. Let's say that 1 plus 2R cosine. Oh, that looks like a plus sign. But it's a -1. Is less than 1. And we're going to subtract 1 from both sides. Let me make sure this is clear what's happening there. Okay, and then when we do that, we're going to end up with and then that ends up becoming R less than 1/2. So basically what this tells us is that our stability is only going, not our stability, our temperature profile equation up here, this guy is only going to be stable for values of R that are less than 1/2. So if you remember when we were using collaboratory to look at this, as soon as we used anything over 1/2, even if it was like 5.1, all of a sudden the temperature profile just like looked absolutely insane and it was squiggly all over and you couldn't see or figure anything out. So that's basically what's happening, and it's because our analysis is not stable for any value over or any R value over 1/2. So what we're going to do in my next video is we're going to see if we can find some alternative method to model our temperature profile that doesn't go absolutely crazy for values that are over R values that are over 1/2. So that's